Hi everyone, this is Dr. Saida Falafini from Cal Poly Pomona. In this video, we want to talk about steady-state probabilities in a queuing system. What is the meaning of a steady-state probabilities and how we can calculate them in a queuing system? We can consider a queuing system as a stochastic system. What does this mean? That means a queuing system, like any stochastic system, has some characteristic of interest that are changing randomly over time. We are interested in monitoring the values of these characteristics of interest and also predict the value of these characteristics in the future. If we look at the bank, for example, as an example of a queuing system, one of those characteristics of interest from the queuing system perspective is how many people are in the bank at any point of time, right? So obviously, if we let's say we are looking at the bank at a specific time, and then someone asks you, okay, how many people will be in the bank, let's say 2 hours from now, right? We cannot say for sure this many number of people will be in the bank 2 hours from now, but since this value is going to depend on how many people will come to the system, how many people will leave the system, so we cannot say for sure how many people will be in the bank 2 hours from now, but we can do some prediction, and we can provide some range in terms of possible number of people that will be in the system at 2 hours from now. Okay, so that's why I call this queuing system is a stochastic system, because there are some characteristics of interest. For example, number of people in the system at any point of time. We don't know exactly how many people will be in the system, but we wanna be able to predict these values so that we can make decisions to see how many people we have to hire, for example, at different times of the day, how big of a space we have to have for the bank, and so forth. So in other words, the number of people present in any queuing system can be one of the characteristics of interest that we want to monitor, and this characteristic of interest is basically the one that is going to form the state of the system. Now, if you remember, for any Markov chain, we also, after we know what are the characteristics of interest that form the state of the system, we also specify the state space. And the state space is telling me all the possible values that the state of the system can get. So if I look at as a number of people in the system as the characteristic of interest, what are those possible values? Obviously, I can go from 0 people in the system, 1%, 2 people, 3 people, all the way to infinity. Okay, so these are the possible values that the state of this system can get. And I can also identify PIJs. Like any stochastic system, I can identify the transition probabilities. And here the transition probability basically is related to going from state I to state J. And let's assume a state I means there are I people in the system, and state J means there are J people in the system. So PIJ basically means that if there are I people in the system at time 0, what is the probability that there are J people in the system at time t? And we show that with probability ijt. And I want you to pay attention to the fact that here in this system, I'm not looking at specific time steps. For example, I'm not looking at the number of people in the bank in every specific hour, right? Because obviously a lot of people will come and go in between the hours. So I want to be able to continuously over time monitor the number of people in the system. Because of that, I can say that a queuing system is a continuous time stochastic process. And it's important to understand really what this concept means, because for every system that we look at in chapter 17, when we look at the Markov chains, those were discrete time stochastic systems. The change in the state of the system happen in discrete points of time. We look at the change in the state of the system in every hour, every day, every month, in the gambling, every hand, and so forth. However, a queuing system is a continuous time. stochastic system, meaning that the change in the state of the system, in the characteristic of interest, happens continuously over time, not at a specific hour or at a specific day and so forth. So it happens continuously over time. So because of that, we basically use this specific notation to identify that if the system is at the state I and time 0, what is the probability that the system goes to a state j in t time unit. And obviously the values of ij, possible values for the state of the system, are coming from this state space set that we already have defined. For example, the probability that if the system is at the state 1 at time 0, there is 1 person in the system at time 0, what is the probability that we end up with, let's say, 7 people in the system at time t? And t is any real number in the time axis, any continuous real number in the time axis. And this type of stochastic systems that can capture the situation of a queuing system in terms of number of people in the system are called basically birth and death processes. Why? Because if basically we consider number of people in the bank, for example, every time a person comes to the system, 1 person is added to the number of people in the bank. So that's similar to a birth in a population. Every time a birth happens, 1 person is added to the size of the population. And every time a person leaves the bank, 1 person is deducted from the number of people in the population. And that's similar to a death in the population. So if when a death happens, 1 person is deducted from the size of the population. And so that's why this whole process of looking at the number of people in the system, number of parts in the manufacturing process and so forth, is like looking at the birth and death process. And this actually birth-death process is a stochastic process that we actually use to study the dynamics of the populations in a country. So that's basically a concept that exists in the stochastic processes. And how the number of people in a queuing system changes, how the number of entities or objects in a queuing system changes, basically falls under the same category as birth-death processes. And as we can see in this definition, to just sum up the definition of birth-death processes, a birth-death process is a continuous time. Stochastic process, continuous time, because the state of the system changes continuously over time. Is a continuous time stochastic process for which the system's states changes at any point of time, and the system's state is a non-negative integer, like the values that we saw, going from 0 people to 1 person, 2 people, 3 people, 4 people, and so forth. So the state of the system is non-negative integer number, and the state of the system can change continuously over time. So that's what the birth-death process is, and that exactly is the situation that happens in a queuing system. Like any stochastic processes, if we can say that the queuing system is a stochastic process, then we have to calculate steady state probabilities pi j. And what does pi j means? If j, which is the state of the system, shows number of people or entities in a queuing system at any point of time, so pi j shows the steady state probabilities for this stochastic system, and it means that what is the probability that in the long run there are j people in the system. And what we wanna, so basically it's basically says, okay, let the system run, let these entities come to the system, let the entities leave the system, and all these transitions happen. And then if we stop the system at any point of time and we look at the number of people in the system, what is the probability that there are j number of people in the system? So that's basically what these steady state probabilities mean. So now we want to see how we can calculate these steady state probabilities, pi j's. Before we calculate the steady state probabilities in a queuing system, let's look at a couple of laws that we are going to consider in our systems. The first law says that every time an arrival happens, the system goes from state j to j plus 1. That means every time that an arrival happens, only 1 person or 1 entity enters the system. and we can call it either arrival or a birth. So every time a birth happens or an arrival to the system happens, we go from system J, for example, to system J plus 1. So at this arrival happens basically at very small time units. So we call it by delta t. So these delta t are very small time units when the arrival happens. Even if the system allows for group arrivals, we assume that these people enter the system in a small time intervals, like one after another. So still in any small time interval at any point of time in the in this stochastic system, only one person comes to the system. So in every birth or in every arrival, there is only one entrance to the system. So and the state of the system is going to increase by 1. The other rule basically, or the other law says that every time a death happens in the system or every time a departure happens in the system is going to go from state J to state J minus 1. And it again says that every time a departure happens, only one person leaves the system. And these departures happen in very small time period. So even if a group of people are going to leave the system, we assume that these departures happen in very small time periods, one after another, and that's how we are going to, for example, let the a group of people leave the system. For the first law, we call lambda j as the rate of arrival to the system when there are j number of people in the system, or when the state of the system is j. So we talk about the fact that for any queuing system, we need to know the rate of arrival to the system, which we show with the Greek letter lambda, and also we need to know the rate of departure from the system, which we show with the Greek letter mu. So in a general system, we assume that the rate of arrival of customers or entities to the system when there are j people in the system is lambda j. Or in other words, we assume that in a general case, the rate of arrival to the system depends on how many people are in the system. And for law 2, we assume that if there are j people in the system, then mu j shows the rate of departure from the system. And again, here as well, the rate of departure from the system depends on how many people are already in the system. And for the time that there are 0 people in the system, we say that, okay, mu 0 is 0, obviously, because there are 0 people in the system, there is no one to leave. So in mu 0, the rate of departure at time 0 is 0. And the last law says that all the births and deaths, or all the arrivals and departures from the system, are independent from each other, so they have no effect on each other. Let's see how I can show this in a general queuing system. So in the queuing system, we have something that we call as rate diagram. So rate diagram is actually very similar to the state diagram that we developed for the Markov chain. So how it's working. So I'm going to show the possible values for the state of the system with this circle. So there can be 0 people in the system, 1 person, 2, 3, 4, all the way to j minus 1, j plus 1, all the way to infinity, right? So then, if you remember in the state diagram in Markov chain, there were arrows between the states, and what we put on top of these arrows were probability of transitions from one state to another. However, what we put in a rate diagram in a queuing system on the arrows are the arrival rates or the transition rates. So what does this show? That shows that if there are 0 people in the system, if the system is in state 0, the rate of arrival of the entities or customers to the system is lambda 0. If there is 1 person in the system or 1 entity in the system, the rate of arrival of customers to the system is lambda 1. And similarly, if there are 2 people in the system, lambda 2 and lambda 3 and so forth. So if there are j minus 1 people in the system, the rate of arrival is lambda j minus 1. lambda j plus 1, and so forth. So as I said, this is a general queuing system in which I assume the rate of arrivals of customers or entities to the system depends on how many people are in the system. That's why if there is one person in the system, I have lambda 1. If there are two people in the system, I have lambda 2. If there are three people in the system, I have lambda 3, and so forth. Okay, so this is a general scenario. And also we have departures from the system, right? So I can go from state 1 to state 0 when one entity leaves the system. And then on this arrow, I also put the rates of departure. So the rate of departure here is mu1, and mu1 means that if I'm at the state 1, then the rate, which means there's one entity in the system, then the rate of departure from the system is mu1. This number of people per hour potentially, or per unit of time potentially, can leave the system. If there are two entities in the system, then the rate of departure from the system is mu2. If there are three entities in the system, the rate of departure from the system is mu3, and so forth. Similarly, if there are j people in the system, the rate of departure is mu j plus 1, and so forth. And as we said before, mu0 is 0. That means when there are 0 people in the system, the rate of departure is 0. So this is the rate diagram for a general queuing system that shows possible values for the state of the system, and what is the rate of arrival to the system, and what is the rate of departure from the system under any possible state of the system. Let's look at one example and see how for a specific queuing system we can develop the rate diagram and what it shows and what it tells us. Okay, in this example we are going to look at MM1 first come first serve infinity system, queuing system. So what does this notation shows? This means that we are looking at a queuing system in which the inter-arrival times of the customers are coming from an exponential distribution. The service times are coming from an exponential distribution. There is one server in the system. The queuing rule is first come first serve. The system has capacity to have infinite number of people in the system, and the population has the size of infinite, so we can just have as many people come as possible to come to the system. Also, we have one assumption. We assume that the rate of arrivals and departures, the rates of arrivals and departures in this system do not depend on how many people are in the system. So this is different from the general case in which we let the rate of arrivals and departures to be different based on how many people are in the system. So if I'm at the state 2, the rate of departure is mu2, and the rate of arrival to the system at that time is lambda 2. But in this example, we assume that the rate of departures and arrivals to the system do not depend on how many people are in the system. So how can I draw the rate diagram? So these are possible values for the state of the system, right? So for any queuing system, the possible values for the state of the system or number of objects in the system is from 0, 1, 2, all the way to j minus 1, j plus 1, all the way to infinity, right? And then the number on the arrows that connect to the states shows the rate of arrivals or departure. And we set the rate of arrivals. I'm going to show the rate of arrivals by lambda and the rate of departure by mu, and lambda and mu do not depend on how many people are in the system. So no matter if there's 0 people in the system or 1% or 2%, the rate of arrival to the arrival of the customers or entities to the system is lambda. Right? And similarly for the rate of departure, no matter how many people are in the system, the rate of departure from the system, the rate of departure from any possible state is mu. So even if I have 2 people or j minus 1 people or just 1% in the system, the rate of departure from the system is mu. So those basically shows that those rates, remember we said the rates are specified in unit of time. So that just shows that in this system, even if there are 2 people in the system or 10 people or 20 people, at this point of time, people live with the system how fast with, for example, average 5 people per hour. Okay, that doesn't mean that exactly 5 people have to leave the system, but that's the frequency or that's the speed by which people leave the system. Now let's look at another example. So in this example, I'm again looking at the queuing system. The inter-arrival times have exponential distributions. The service time has exponential distribution. There are 3 parallel servers in the system. The queuing rule is first come, first served. And the size of the system is infinity. I can have as many entities as possible to come to the system. And the size of the population from which these entities are coming is infinity too. So now I want to draw the rate diagram for this queuing system. So like any other queuing system, the possible values for the state of the system is 0% in the system, 1%, 2, 3, 4, 5, 6, all the way to infinity, right? So now I need to draw the arrows between the states and just specify the rate on top of the arrows. So I assume that the rate of arrival to the system is not going to depend on how many people are in the system. So no matter if there is 0% in the system or 1% or 2 people and so forth, the rate of arrival of the customers to the system is lambda. So that shows the speed of arrival of the customers to the system. So for example, in a bank, customers arrive to the system with the rate of 10 per hour on a For example, in a bank, the customers arrive to the system with the rate of 10 per hour, no matter how many people are in the bank. So that's the speed or the frequency of arrivals of the customers to the system. Okay, we are good in terms of the capturing the arrival of the entities to the system. How about the rate of departures from the system? I want you guys to pay attention to the fact that we have 3 parallel servers in this system. What does that mean? So we have server 1, server 2, server 3, and this is basically the queue in which the entities are going to wait. So entities are going to come to the system with the rate of lambda, and now we want to see the rate of departures. So pay attention to the fact that when we specify the departures, these values that we put on these arrows are the rate of the departure from the system. So if we consider this to be the whole system, so this is the rate of departure from the system. The lambda is the rate of arrival to the system. Mu is the rate of the departure from the system. So we need to specify the rate of the departure from the system. Those numbers that we put on the general queuing system example, when we put, for example, mu1 or mu2, mu3 and so forth in the general example, these are the rate of the departure from the system, which means if there is 3 people in the system, then this is the rate of departure from the system. Okay, so that's exactly what we have here. Now let's assume the rate of the departure from each one of these machines in the system or each one of these servers is mu. What does that mean? That means this server can provide service to mu number of entities per unit of time. That's also the rate of departure from this server 2 and similarly for server 3. Okay, so let's see now, given the fact that we know the rate of departure from each one of these servers, how we can identify the rate of the departure from the system. So if the system is at the state 1, what does that mean? If the system is at the state 1, it means there is 1 person or 1 entity in the system. And let's assume that entity is in any one of the machines. So let's assume that entity is in machine 1. Okay, so in that scenario, then the entity is in machine 1 and machine 1 is the only one that is working, and the rate of the departure from machine 1 is mu. So the rate of the departure from the whole system is mu. Now let's assume that we are at the state 2, which means there are 2 people in the system. And let's assume these two people, obviously if they are in the system, they're not waiting in the queue, right? The servers are empty, so they have to definitely go to the servers to get the service. So if there are only two people in the system, we have 3 servers, so definitely these 2 people just can go and get the service without waiting or anything. So let's assume one of them goes to server 1 and one of them goes to server 2. And we know the rate of departure from server 1 is mu, and the rate of the departure from server 2 is mu. So the rate of the departure from the whole system is going to be 2 mu. So this is if you want to get a better sense, just assume that I have a machine, and this machine can process, let's say, 10 parts per hour. And I have another machine, and this machine can also process 10 parts per hour. So if you want to consider the rate of exit or departure from this whole system, it's not 10 parts per hour, because this machine produces 10 parts per hour, this machine produces 10 parts per hour. So the rate of the departure from the whole system is going to be 20 parts per hour. Okay, so that's exactly what it happens here. How about having 3 entities in the system? So if I have 3 entities in the system, they obviously are not going to just stay in the line, because I have 3 servers and all these servers are empty. So these 3 entities just go to the servers to get the service. Okay, and server 1 has the rate of departure of mu, server 2 has the rate of departure of mu, and then server 3 has the rate of departure of mu as well. So what is the rate of departure from the whole system? The rate of departure from the whole system is going to be 3 mu. Okay, so in that scenario, the rate of departure from the whole system is 3 mu. Now let's see, how about if we have 4 customers in the system or 4 entities in the system? If I have 4 entities in the system, obviously 3 of them will go immediately to the servers 1, 2, 3, because those servers are empty. So these customers just, or these entities immediately goes to the customer, to those servers. However, another entity is going to stay in the line because all these servers are full, so this entity has to stay in the line. So then what is the rate of departure from the system? Still, server 1 is busy with the rate of departure of mu, server 2 is busy with the rate of departure of mu, and server 3 is busy with the rate of departure of mu. So the rate of departure from the whole system is still 3 mu, because this person that is waiting in the line is not basically pushing for anything, so they are just waiting in the line. So the rate of the departure from the system is 3 mu. So if there are 4 people in the system, then the rate of the departure is going to stay as 3 mu. Similarly, if there are 5 people in the system, 2 of them are going to stay in the line, 3 of them are going to go to the servers. Still the rate of the departure from the system is 3 mu, and for 6 people 3 mu, and so forth. And basically this is the diagram rate for this specific queuing system with 3 parallel servers. And one thing we know about the birth death processes, which basically capture the whole structure of the queuing systems, is that for most of these birth death processes, the inter-arrival time of the customers and also the service time of the entities follow exponential distribution. So now we know enough to be able to calculate the steady-state probabilities in a queuing system or for a birth-death processes, which is basically the umbrella that also covers the queuing systems as well. So let's look at the general queuing system. So we are going to basically extract the steady-state probabilities for a general queuing system, then we can customize the formula for any specific queuing system that we are going to look at. So for a general queuing system, this is the rate diagram that we developed initially, right? Obviously, it's a queuing system. Then the possible values for the state of the system is 0 entities in the system, 1, 2, 3, all the way to infinity. And we assume that in a general scenario, the rate of arrivals to the system depends on the number of entities in the system, and the rate of departures from the system also depends on the number of entities in the system. That's why I use lambda 0, lambda 1, lambda 2, all the way to lambda infinity, as well as mu 1, mu 2, mu 3, and so forth. So we can say that for any queuing system, entities come to the system, entities leave the system. So we go from any state J to J plus 1 to J minus 1. So all this transition happens over time. But in the long run, in the equilibrium, in the steady state, the average number of times that we go out of one possible state equals to the average number of times that we go into that state.